Today topic is wired LAN, that is Ethernet. We are going to see the Ethernet. In this topic, we are going to cover the IEEE standard, standard Ethernet, changes in the standard, fast Ethernet, gigabit Ethernet, and wireless LAN IEEE 802.11. So the Institute of Electrical and Electronic Engineer is called as IEEE. It published severally widely accepted LAN recommended standards. So that standard could be called as various IEEE 802 standard. First one is IEEE 802.1 high level interface, that is MAC bridges. And then we are having a logical link control, CSMA CD, token bus, token ring, metropolitan area, broadband LAN, fiber optic LAN, security, wireless network. Those are comes under a IEEE 802.123 that is going on. And then we are going for a IEEE standard. So it is a IEEE, it is mainly equipped by the variety of manufacturers. ISO only approved 802 under the designation of ISO 8802 and it's adopted by ANSI in 1987. In this we are going to see a data link layer. So data link layer in the IEEE standard is divided into two sub-layer. One is LLC and another one is MAC. So relationship between 802 with OSI model is called as, so we are having a upper layer, data link layer, physical layer. I already told you that we are having a LLC and MAC. So this is the two types we are having in this. So first one is logical link layer. So in logical link control, it handles framing, flow control, error control. In IEEE 802, flow control and error control are the part of framing duties. It can be collected into a logical link control. Framing is handled both LLC sublayer as well as we are going to use in a MAC sublayer also. The LLC provides only one single data link control protocol for all IEEE LANs. And then in this we are having two things. One is framing and what is the need of LLC. So framing means it defines a protocol data unit and the header contains a control field like the one in HDLC. This field is used for flow and as well as error control. In header we are going to use a DSAP, that is destination service access point. So I'll show the diagram of that. So see here we are having a DSAP and then we are having a SSAP. So DSAP and SSAP we are going to added in this header fields, that is destination service access point and the source service access point. So what is the need for LLC here? The purpose of LLC is to provide flow and error control for the upper layer protocol. So however, the most upper layer protocol such as IP do not use the services of LLC. And then in medium access control, IEEE project 802 has created a sublayer. It is called as media access control that defines a specific access method for each LAN. It defines CSMA CD collision detection in the media access method for Ethernet LAN and the token passing method for token ring and token bus LAN as well as. So and then in physical layer we are going to use a dependent on the implementation and the type of physical medium is used. IEEE defines detailed specification for each LAN implementation. So in IEEE standard 802.3 we are having some generation. First generation is standard Ethernet, that is 10 Mbps. Second one is fast Ethernet, that is 100 Mbps, and third one is gigabit Ethernet 1 Gbps and 10 gigabit Ethernet is 10 Gbps. So in this we are having a MAC layer and then physical layer. So we are going for a MAC address. The frames data received from the upper layer and passes them to the physical layer in frame format of MAC layer. We are having that Ethernet does not provide any mechanism for acknowledging received frames, making it what is known as unreliable medium. And then this is the frame format. We are having a permeable SFD destination address, source address, length or type, and data padding and CRC. First we are going for a frameable. So a 7-byte pattern of alternating zeros and ones used by the receiver to establish bit synchronization. Each frame contains the bit pattern 10101010. The pattern provides only an alert and a timing pulse. The preamble is actually added at the physical layer and is not part of the frame. And the next one is SFD, that is a start frame delimiter. The sequence 10101011, which indicates the actual start of the frame and enables the receiver to locate the first bit of the rest of the frame. And the next one we are going for a destination address. The DA field is 6 bytes and specifies the station for which the frame is intended. It may be a unique physical address, a group address, or a global address. And then we are going for a source address. So the field is also 6 bytes and contains a physical address of the sender of the packet. And then length or type, we are going for a length or type. It will be length of LLC data field is in octet or ethernet. Type field depending on whether the frame conforms to the IEEE 802.3 standard or earlier ethernet specification. In either case, the maximum frame size excluding preamble and SFD is 1518 bytes. And then we are going for a data units supplied by LLC. It is a minimum of 46 byte and a maximum of 1500 bytes. CRC, we are going for CRC. This field is contains a error detection information. And we are going for a frame length. An Ethernet frame needs to have a minimum length of 512 bits or 64 bytes. Part of this length is the header and the trailer. So it shows the minimum and maximum of the frame. So in this, if we count 18 bytes of the header and the trailer, that is 6 bytes of SA plus 6 bytes of DA plus 2 bytes of length plus 4 bytes of CRC, then the minimum length of the data from the upper layer is 64 minus 18 is equal to 46 bytes. So if the upper layer packet is less than 46 bytes, padding is added to make up the difference. The standard defines the maximum length of a frame without preamble and SFD as 1518 bytes. If we subtract the 18 bytes of the header and trailer, the maximum length of the payload is 1500 bytes. And then we are going for addresses. A source address is always the unicast address, and then the frame comes from only one station. The destination address can be unicast, multicast, or a broadcast. So if at least a significant bit of the first byte in a destination address is 0, the address is unicast. Otherwise it is a multicast. So we are going for a access method, that is CSMA. CD we are going to use here means, so standard Ethernet uses one persistent CSMA per CD. Slot time is equal to round trip time plus time required to send the jam sequence. That is maximum length is equal to propagation speed into slot time divided by 2. And the next one we are going for a physical layer. So in physical layer we are having some specification here. So we are going to use a 10 base 5 and then 10 base 2 and then 10 base T and then 10 base F voice we are going to use here. So 10 base 5 means we are going to use for a coaxial cable, and then 10 base 2 wire is for thin coaxial cable, and 10 base T is used for UTP, and 10 base F is used for star topology and then fiber optic cables. So next one we are going for a encoding in a standard Ethernet implementation. So in encoding we are going to see Manchester encoding. So we are going to use some using nowadays we are using a Manchester encoding as per IEEE 802.3. In order to transport digital bits of data across carrier waves, encoding techniques have been developed, each with their own merits and demerits. So, digital signal is a sequence of discrete, discontinuous voltage pulses. So, data is represented in binary, and this binary data is transmitted by encoding each data bit into a signal elements. So, we are having some properties of encoding techniques. What is that means? Synchronization capability, and then unity to noise. The ability to stay synchronized or to get resynchronized. Error detection capability, and then ability to separate noise from the transmitter signal. So in Manchester encoding, each bit period has both the high and low voltage valves. If the data is 1, the first of the bit time period is sent at the positive level and the second half of the period is at the negative level. For a data bit of 0, first a negative signal and a positive signal. There is a transition which can be used for a synchronize also, and sometimes this method is called self-clocking encoding method. So encoding waveform for a 8-bit data stream is called as double one triple zero 101 is called as. And the next one, 10 base of 5. We are in 10 base of 5, we are going for a thick ethernet cable. So this is a thick ethernet cable we are going to use here. So 10 base 5 means 10 mbps, and then baseband is digital and 500 meter. We are going to use this cable as thick coaxial cable. And next one is 10 base 2 thin ethernet. So in this we are going for a 10 base 2. 10 means 10 mbps, and then base is digital, and 2 means 185 meter. So here the meter is calculated in this place. So thin coaxial cable we are going to use here, and then we are using a bus topology, and then this is called as a 185 meter. Next one is twisted pair cable. So that is 10 base T. So in twisted pair cable we are going to use 10 is a mbps, and then baseband is a digital, and T is a twisted pair. So here 10 base T hub is used for 2 pairs of UTP cable, and then collision occur in the hub. Maximum length of cable is only a 100 meter. And then next one we are going for a fiber ethernet. So here we are using a star topology. 10 base of F, 10 is mbps, baseband is digital, F is called as a fiber. So here we are using a hub, and then 2 fiber optic cables we are going to use for a joining purpose. And then this is a summary of Ethernet implementations. So media, maximum length we are going to use here, and what is a line encoding. So always we are using a Manchester encoding only. So and the next thing we are going to see is a bridged Ethernet, and then switched Ethernet, and full duplex Ethernet. Bridged Ethernet means we are having two effects on the Ethernet. First one is raising the bandwidth, and then separating collisions domains. So in bridged Ethernet, without using the bridge in the Ethernet networks, just you see the diagram here. So without using the bridge in the Ethernet network, the total capacity is shared among all the station with the frame to send. So that station share the bandwidth of the network. And the next one is, if only one station has frame to send, it benefits from the total capacity. But if more than one station needs to use the network, the capacity is shared. And then we are going for a without bridge. A bridge divides the network into two or more network, and bandwidth wise each network is independent. And then separating collision domains. So what is mean by separating collision domains? Here we are going to use by the help of bridge we are going to see the avoid the collision domain also. Next we are going for a switched Ethernet. So in switched Ethernet, the idea of a bridged LAN can be extended to a switched LAN, and then the layer 2 switch is an N port bridge with additional sophistication that allows faster handling of the packet. So by the help of switch only we can able to do this. So it is called as a full duplex Ethernet. And the next one we are going to see here is 10 base 5 and 10 base 2 we are going to use for the op duplex method. So a station can either send or receive, but may not do both at the same time. So the full duplex mode increases the capacity of each domain from 10 to 20 mbps. Full duplex Ethernet uses two lines. One is one to transmit, and another one is one to receive. And then there is no need of CSMA CD method. So in full duplex method, each station is connected to the switch via two separate links. So each station or switch can be sent and receive independently without worrying about collision. Each link is a point-to-point dedicated path between the station and the switch here. So see here we are having a transmit and as well as receive here. And the next one we are going for a fast Ethernet. So in fast Ethernet, it is backward compatible with standard Ethernet. In this we are going for a upgrade the data rate to 100 Mbps and then keep the same 48-bit address and then keep the same frame format and make it compatible with the standard Ethernet and then keep the same minimum and maximum frame length also. So in this we are going to use a topology is point to point and then star topology we can able to do this. So in this max sublayer also we are going to implement here. So next one is in physical layer we are going to use some topologies, that is point to point or switch here. And the next one is fast Ethernet implementation. For this implementation we are using a two types of wire here, 2 wire or 4 wire we are going to use for a connection. So this is a example of a wire. Next one we are going to see a gigabit Ethernet. So in gigabit Ethernet we are having some goals. So to upgrade the data rate to 1 Gbps and make it compatible with standard or fast Ethernet and use the same 48-bit address, and we have to use the same frame format also and keep the same minimum and maximum frame length in a gigabit Ethernet. So this is the goals we are going to see in this. And then next one is in full duplex mode there is a central switch connected to the all computers or other switches. Each switches as buffer for each input port in which data are stored until they are transmitted. So there is no collision in this mode. And the next one we are going for a carrier extension, full duplex mode, and then frame bursting. So frame bursting is nothing but to transmit short frame. Each frame carries redundant data. Multiplex frames are sent and these multiplex frames look like one frame. Padding is added between the frames is called as a frame bursting. And the next one is topology. In gigabit Ethernet physical layer we are going to implement by the help of topology only. So we are having a star topology, means by the help of switch only we can able to connect the node here. So without a switch we can't able to connect the nodes. So that is the criteria we are going to use for a implementation. And then next one we are going for a IEEE 802.11. So in IEEE 802.11 we are going to see some wireless LAN also. So in this it's referred to a family of specification developed by a IEEE for wireless LAN technology. So it is full and full wireless LAN technology only. So and then in this we are going to see a architecture, max sub layer and a physical layer. So what is the architecture of 802.11? So in this we are having a BSS and then extended service set. One is BSS means basic service set. Second one is extended service set. So basic service set is the basic building block of IEEE 802.11 architecture. A BSS is defined as a group of stations that coordinates their access to the medium under a given instance of the medium access control. And then BSS without an AP is a standalone network and cannot send to the other BSS. A single BSS can be used to form network and cannot send data to other BSS, and a group of station within the range of each other also ad hoc network or typically temporarily in nature. So we are going to use that also. So in this diagram we are going to see extended service set. So in this we are having a distributed system and then we are having a AP here, and by the help of access point we are going to access the all the nodes here, and then we are having a server or gateway in this. And the next one we are going for a distributed coordination function, so that is DCF. So it is a basic access method used to support asynchronous data transfer on a best effort basis. And then wireless LAN cannot implement CSMA CD for three reasons. One is for the collision for collision detection, a station must be able to send data and receive collision signals at the same time. Collision may not be detected because of hidden station problem. And then this is the diagram for CSMA CA flowchart. So we are going to start here, and then it will be go for a setback of to 0 and persistent strategy, and then we are waiting for a DIFS, and then we are going to send the RTS and then set a timer, and then we are going for a CTS received before timeout, and then wait for SIFS, and then we are going to send the frame and then set a timer, and it is going for a acknowledgement received in a timeout or so this is the how we are going to see the success or abort operation by the help of CSMA CA flowchart only. And then see the diagram of this. We are using RTS as well as we are using a CTS SIFS, and then we are going to get the acknowledgement here. So next one is a network allocation vector. So in network allocation vector, so when a station sends a RTS frame, it includes the duration of time that needs to be occupied the channel. Next one is collision during handshake. Handshake means we are going to send the data and then we are going to get the acknowledgement. After the we are going to get the acknowledgement, we are going to again start the process here. So that is called as a handshaking. We are studied in three-way handshaking in a TCP mechanism. And the next one is PCF, point coordination function. So it is mainly used for the same time of station wants to use only DCF and then AP wants to use PCF, means we are going for a point coordination function. This is a fragmentation frame format. In this we are having a FC. FC means frame control. So frame control is defined as 2 bytes long and defines the types of frame and same control information. And then this is a field we are going to use in a IEEE 802.11 max sublayer. We are having a version type, subtype, and then DS. From DS what we are going to do here, and then more flag, what is the retry, and then power management, more data, and then WEP, that is wired equivalent privacy, and then reserved also we are going to use here. So this is the frame format we are going to use, and then we are having a types of frames also, that is management frame, control frame, data frame. This is considered as a HDLC. We are taking this frame format by the help of HDLC. Remaining we'll see in next class.